Hey everyone, thank you for joining us for this presentation on why use an RMBS by AMETEK Solidstate Controls. My name's Craig Williams. I'm the Senior Technical Manager based in Houston, Texas. So the objectives today are going to be understand a UPS system that has an internal bypass switch. In other words, it's integral to the UPS itself. It's not outside of the UPS cabinet. Understand the need for complete isolation for electrical safety, and discuss the advantages of an RMBS, a remote manual bypass switch, which is completely external and separate to the UPS system. Okay. So first of all, this diagram here shows you a double conversion industrial UPS. And with double conversion, what it means is we have a rectifier that converts the AC into DC, and then an inverter that converts the DC back into AC. That is what double conversion means, okay? And you can see on the left-hand side, we have our AC input voltages, 480 volts AC for North America into the battery rectifier. And if it's a single phase output UPS, then you're going to have a single phase bypass source as well. And then in this system here, we have a battery that is 120 volts, which is once again pretty much standard for North America for a 60 cell lead acid battery. But the most important thing that you can see here is the manual bypass switch is inside this box here. And this box here, excuse my terrible drawing, that box there is the actual UPS itself. Anything within those hashed lines are inside the UPS. So for this system here, the manual bypass switch is inside the UPS, and that becomes very important in just a moment. And also on this page, I'd like to refresh everybody the difference between a static switch and a manual or maintenance bypass switch. The easiest way to understand it is that a manual bypass switch is usually a mechanical switch. In fact, it near enough always is a mechanical switch. It can either be an arrangement of switches, or for AMETEK Solidstate Controls, it is a rotary switch that has make before break contacts in it. So it's an actual switch that mechanically makes and breaks the circuits. The static switch is an electronic switch, which it's actually drawn identical to what it actually is. It has two SCRs back to back connected in inverse parallel. And what that allows us to do is, if we send a signal to the gates of both of those SCRs, we can allow, if there is a sine wave on this side of the static switch, if we send a signal to the SCRs, that turns that switch on electronically. There is no moving parts in it whatsoever. It's just using the semiconductor devices, which are the SCRs, and it allows the sine wave to pass through to the other side of the switch. So static, as in no moving parts. It is completely semiconductor and electronic driven for a static switch, and for a manual bypass switch or maintenance bypass switch, it is nearly always a mechanical switch that has moving parts. Okay. Now, the power flow for a double conversion industrial UPS is, if you follow the red lines there, that's the power flow in normal operation. And the green line is the power is energized and ready to go if necessary. So on the bottom here, you can see the power flow is from the AC input into the battery rectifier, battery charger rectifier. That converts the AC into DC to whatever the battery needs to be charged at. The battery is then trickle charged, but the majority of the DC power is going to go to the inverter, and that inverter converts that DC back into AC. That goes into, for an industrial UPS, it will go into an isolation transformer, and then that goes into the static switch, and this static switch will be on. We call this the inverter static switch, and this one up here is the bypass static switch. So the inverter static switch is on and the bypass static switch is off. And then that power then flows through the manual bypass switch, which is internal to the UPS and out to the load circuits. So that is the basic operation, the normal operation of a double conversion UPS. Okay, let me erase that. Now, if we have a power failure, an AC input fail, we can see here we've lost our AC input, then the batteries take over. We do not switch to battery. The batteries are in parallel with the charger. So when we lose power to the charger, the batteries just continue to supply the DC to the inverter. The inverter has no idea, in truth, that the charger has failed. All it cares is that there is DC at the input, whether it's from the charger or whether it's from the battery. Obviously, it has to be of a substantial voltage within the ratings of the inverter itself. For our UPSs, for AMETEK Solid-State controls for a 60-cell system, that is going to be between 105 and 140 volts DC. But as long as we have a battery here, we are good. And then everything else remains the same. The load circuits don't see any change whatsoever. The inverter still converts that DC back into AC. This static switch still remains on. This manual bypass switch is still in this position. And everything is as if there isn't a power outage, except for the charger is not working anymore. Now, most UPS manufacturers have to have some form of ability to be able to disconnect the battery if the battery discharges too far. So if this power failure that we have here goes on for too long and discharges the batteries, and in most circumstances it's down past 1.75 volts per cell for a lead acid battery, and that for a 60 cell battery would be 105 volts DC. So we have a tripping mechanism within our system that it says, okay, my battery has got to 105 volts DC. I need to do something about it. And on the next page, I'll show you exactly what happens. And what happens is, first of all, the UPS itself says, okay, my battery has got too low. I need to transfer to bypass supply. So it turns this bypass static switch on, and then only when that switch is on, it will then turn the inverter static switch off. Okay? And then as soon as it has done this, it says, and now I am going to trip the battery input breaker to prevent the battery from feeding power into the inverter. Hopefully that makes sense, what happens when the battery discharges too far. And then last but not least, the difference between static bypass and manual bypass in this system. What we can do is if you saw on that previous page, we were in static bypass going through the static switch. But now we're going to move this manual bypass switch position to the bypass position. Okay? And in doing so, we make this connection here before we break that connection there. That's done internal within the switch itself. It's a make before break switch. And therefore you can follow the red there. That will be the power flow to the system. Okay? But there is a problem with this design. And here's a better drawing where you can see all the input terminals to one of our UPSs. So, and here's the bypass switch that we just mentioned there. And this is in the bypass position. Actually, I made one minor mistake. That is actually closed. So when we have it in this position and the power flow, this is coming from your bypass, from your MCC, and it flows into the UPS through the bypass switch and back out to your load circuits. Okay? Internal to the UPS. So within an AMETEK solid-state control UPS, wires 1, 10 and 15 are still going to remain live or hot, and wires 199 and 15 are still going to be live or hot. Okay, yes, you can disconnect the battery. Yes, you can disconnect the 480 volts at the upstream MCC, but you cannot go and work in the inverter, battery charger, or static switch safely, because you still have power here at the terminals inside the UPS itself. So you can't deem this cabinet to be volt free to go and do work. Hopefully that shows you what the downfall of having an internal bypass switch is. Let me erase this again. Okay. And it's very important, especially in North America. Now there are different guidelines and regulations for many other countries around the world, and they all follow essentially the same thing, and that is you must be able to lock out, tag out a system and make it volt free for workers, so they are not going to be injured. And the OSHA requirement in North America is this one here, 29 CFR 1910-147. Okay, and that is for general industries, outlines measures for controlling different types of hazardous energy using LOTO, lockout, tag out. Okay, and then you can see down here the energy control program. Any employer should establish a program that consists of energy control procedures, employee training, and periodic inspections to ensure that before any employee touches anything within either a mechanical or electrical piece of machinery that could be unexpectedly energized, started up, or have release of stored energy, that the machine or equipment shall be isolated from the energy source and rendered inoperative. That is what the OSHA Energy Control Program says. And more specifically, one of the rules that many people don't understand is 1910.147C23. After January 2nd, 1990, whenever the replacement or major repair of any piece of equipment has been performed, or when new machines or equipment are installed, energy isolating devices for such machines or equipment shall be designed to accept a lockout device. So basically, whenever you do any major maintenance or install new equipment, you should be able to lock out and tag out that system and make it volt free. That's pretty much what that rule is saying. And to be able to do that, what you can do is you can install an RMBS cabinet or a remote maintenance bypass switch. Okay, now let me explain this drawing. This drawing is exactly the same drawing that we had before. We have this UPS here, and it has this internal maintenance bypass switch here. And remember, if we used that, these terminals here would still be hot, even if we go to maintenance bypass and isolate the battery and the AC input. But what we can do is, with the addition of an external RMBS, we can in fact make that system volt free, and we'll show you how. So in normal operation, you can see here the power flow is as normal, through the rectifier, through the inverter, through the static switch, through the internal bypass switch contact, out through into the RMBS cabinet, through this contact here, and out to the load circuits. That is where the power flow flows. And we still have our bypass, our 120 volts bypass, coming into the RMBS cabinet, through this closed contact here, through the bypass switch internal to the UPS, and it's ready to go at the static switch here if necessary. Okay, that is when we have the RMBS in position 1 and everything is in normal operation. Okay, hopefully that makes sense while I erase all of this. Now, if we want to make this UPS volt free, the first thing we need to do is transfer the static switch to the bypass position. So you can see we have now pushed the bypass to load button on the front of the UPS, and power is now flowing from the bypass still through this contact. We're still in position 1, nothing has changed there, and we're now going through the static switch in the UPS. The inverter and the charger are still energized, but they're not supplying power anymore. The bypass is supplying the power to the load circuits. Okay? And there's a good reason why we always transfer a system to static bypass before we move the switch to position 2. And I'll explain that in just a moment. Because the next thing we're going to do is move to position 2. And what that does is it closes this contact here. And let me go back to the previous page. Okay, so you can see on this side of the contact here, we're going to have the 120 volts AC from the bypass. Okay, and if you follow that, that also goes all the way down here. So on this side of the switch, you're also going to have 120 volts from the bypass. So it is the exact same voltage, phase relationship, frequency, everything is identical because it is the same power source. So when we go ahead and we change the position of that switch to position 2, what we do is we make this contact here and then we break this contact here. So that allows us to have a seamless transfer of power. So now power is actually flowing through here, down through that contact and out to the load circuits here. Yes, we do allow bypass to go back into the UPS. That's more for testing purposes now. Sorry, testing. When we're in position 2, the factory trained FSE can go and do some testing if necessary. But in this position, we are now what we call in maintenance or manual bypass. Okay. And then what we can do is we can go in and we can shut down the UPS following the procedure on the front of the panel. And that will include turning off the AC input to the rectifier, turning off the battery input here. And then what you will have to do is, hopefully you have an external disconnect here. You will have to open that. And then you will have to go back to this MCC back here. And you will have to isolate the 480 volts there. Okay. Now that will make those two sets of contacts volt free. But we still have power on this contact here and we need to remove that. So the way to do that is to go to position 3 that you can see at the top right hand corner here. And what that did was that opens this contact here. So we still have power flowing through this contact here out to the load circuits. But now this contact is open, this contact is open. We have no power on these terminals. We have no power on these terminals, no power on these terminals, and no power on these terminals. And in truth, you could actually completely remove this UPS, install another UPS. It could be a different manufacturer, it could be a same manufacturer, a different model, whatever. And then you could do that while the load circuits are maintained by your bypass. You'll never lose power. That just shows you the flexibility that having an RMBS gives you. It allows you to do complete maintenance. You can replace the inverter bridge, all the capacitors. You can replace all the capacitors and fans in the charger, replace control boards, all very, very safely because there is now no power in this UPS whatsoever. Okay, that is why the RMBS cabinet is a very, very good idea. And like I said, you can have an AMETEK SCI RMBS cabinet installed on the output of any manufacturer of UPS. They're not directly linked. You don't have to have one particular manufacturer of bypass switch for one particular version of a UPS. The RMBS cabinet, it does have some connections that you can, if you wanted to, have some options that connect back to the UPS and give alarms. But for the standard, being able to make your UPS volt free, you can use an AMETEK SCI RMBS cabinet on any UPS manufacturer that's out there. Okay, and as I said, all terminals on the UPS are now volt free. And then returning the UPS back to service, the first thing we do is move the bypass to the position 2. What that does is that puts bypass back into the UPS cabinet, and that usually supplies power to the control boards and allows us to start to follow the startup procedure for the UPS. We will have to then remove the lotto that was at the MCC for the 480 volts in America, and also from the battery disconnect that came in there, the external battery disconnect. Okay, we need to remove that lotto. Then we will start the UPS up following the procedure designated for that UPS. And that will then start the rectifier, it will start the inverter, and it will be ready to supply power when necessary. But power flow is still going through this contact here. Okay. And then at this point here, I mentioned earlier that in position 2 we can test the static switch. So that's what we're going to do next. We can test this static switch. We can press inverter to load, bypass to load, and make sure that it transfers within the UPS itself. Now remember, this contact here is open, so it's not going to do anything to the load circuits. The load circuits are still powered through this contact here, but we can test the operation of the UPS when we are in position 2. Okay. And then what we need to do is return the static switch to the bypass position, because we are getting ready now to move to position 1. And when we move to position 1, we are going to make this contact, and then we are going to break this contact. So we need to make sure that both sides of this switch are the same voltage and power. So we have bypass here, and we have bypass on this side here. They are identical. You can't go wrong. Okay. So when we go to position 1, we're still in static bypass, but we are now in normal operation on the RMBS. Power flow now goes through the UPS, through the static switch, and back out this way here to our load circuits. And then the final thing that we have to do is move the static switch to the inverter to load position, and we do that by pressing the inverter to load push button on the UPS, and now we're back in normal operation. Unfortunately, I made a mistake here. That's open and this one here is closed. My apologies. Power flow is back to normal this way here. We now have battery backup if we had a power failure. Okay, so that is the advantages of installing an RMBS. And what I'm going to do now is show you a video of us working in the lab on an actual RMBS system connected to a UPS, and we captured the oscilloscope transfers going from bypass on the static switch to RMBS bypass and backwards, and we captured the transfers, and we'll show you them to make sure there is absolutely no break in the output voltage and current whatsoever. Hopefully you enjoy it. Take care until next time, and thank you for watching. Okay, so today we're going to show you a seamless transfer using an RMBS, a remote manual bypass switch, and we've got an oscilloscope and a Fluke 87 meter connected to the output terminals of the bypass switch. So these are the terminals that go to the load circuits. As you can see, the meter up here is showing you 122.9 volts. The oscilloscope is going to capture the transfer, and basically what we've done is we've connected to the contacts that are related to this switch, and when those contacts change when we move this switch, it's going to trigger the scope and capture the before voltage and the after voltage, and then you can see that there is no break in between when we go from normal operation to bypass operation, and then we will do the same. We'll go from bypass operation to normal operation. Okay, so we've got everything set up on the oscilloscope. So what I'm going to do now is I'm going to go from the normal position to the bypass to load position. And as you can see on the screen there, the red going down, that is when the trigger from the contact disappears. So that's when the actual transfer took place. So you can see the before voltage, the blue sine wave is the output of the system, and you can see that it's all good up until this point here, and you can see there is absolutely no distortion, no gaps, no break at all when we go from normal to bypass. And then all I need to do is change the slope position, and now we want it to trigger on going up the way. So when I go from bypass to load to normal operation, just like that, you can see once again when the red changes state, that's when the contacts in the RMBS switch changed state. And you can see once again, prior to the change of state, the AC waveform is absolutely perfect. During and after, it stays exactly the same. So this proves that whenever you go between normal to bypass operation, there is absolutely no break in the output supply. It is a make before break transition inside this switch, and you should have no problems. So the RMBS is a really good addition, not only to AMETEK Solid-State Control UPSs if you only have an internal maintenance bypass switch, but any other UPS manufacturer that only has a maintenance bypass switch that is integral to the UPS itself. If you put one of these remote manual bypass switches on the outside of that, then it allows you to make your UPS completely volt free to do maintenance on it. Thanks for watching. Take care till next time.